This is our second video in our study of patterns among the primes. Here we'll study the cycles of gaps that arise at each stage of the Eratosthenes sieve. So we begin with Eratosthenes sieve, and we introduce the cycle of gaps that occurs at each stage of the sieve, and we'll use this notation, the cursive G of P primordial. This notation, P primordial, it's important. You'll see it often in this study. The primordial is the product of all the prime numbers up to including P. So that's that P sharp is P primordial. And you can see at the bottom there, it grows very quickly. The primordial is like the factorial. You may be familiar with that, but the product is only over the prime numbers. So Eratosthenes sieve. Let's start with the basics briefly. So we list the natural numbers up to some bound. We mark 1 as a unit. And then we repeat the following. Confirm the smallest remaining number as the next prime and cross off all multiples of this new prime from the list. And then repeat. And we continue this until all the listed numbers are crossed off or confirmed as primes. So let's take a look. We've marked 1 as a unit. We confirmed 2 as a prime. And so we cross off all the multiples of 2. That's all the even numbers. The smallest remaining number is 3. So we confirm 3 as a prime. And we mark off the multiples of 3. So 9, 15, 21, 27. The smallest remaining number is 5, is now 5. So we confirm 5 as a prime number. And then we mark off the multiples of 5. So 25 comes off the list. Eratosthenes sieve is one of the oldest. It's an ancient method of finding all the prime numbers in order. So here we now look at, let's return to Eratosthenes sieve and let's look at the gaps. Let's start looking at the gaps. So let's go back to 2. We go back to 2, and after we have confirmed 2 is a prime, we have a pretty trivial cycle. The cycle of gaps here is just the number 2. Jokingly, the big insight here is that all odd numbers differ by 2. There you go. So we have the cycle of gaps. That cursive G at 2 primordial is just a single gap 2. The length is 1 gap, and the sum of that gap is 2. When we confirm 3 as a prime and take out the multiples of 3, now the cycle consists of 2 gaps, 4 followed by 2, and this span is 6. I do want to call your attention to what's going on at the front of Eratosthenes sieve. That first gap goes from the unit 1 to the next unconfirmed number. So we skip over the confirmed primes. So our cycle 4, 2, that first 4 jumps from 1 to 5, and then 2 to 7, 4 to 11, 2 to 13, and so on. At 5, the cycle starts to get interesting. The cycle of gaps for 5 primordial is 6, 4, 2, 4, 2, 4, 6, 2. There are now 8 gaps in the cycle, and its span is 30. The sum of the gaps, the span, is 30. So after we have confirmed 2, 3, and 5 as primes and removed their multiples from the list of numbers, all of the remaining numbers will differ by this recurring cycle. 6, 4, 2, 4, 2, 4, 6, 2, and then again 6, 4, 2, 4, 2, 4, 6, 2. The next remaining number, 7, we confirm it is a prime. Now the cycle of gaps starts with 10 and then 2 and 4 and continues that way, bigger than we'll note here. So here's our cycle of gaps at each stage of Eratosthenes sieve. The first gap in the cycle jumps from 1 to the next prime, passing over the confirmed prime numbers. The length of this cycle is always, that's Euler's phi function, phi of p primorial, and the span is always the sum of its gaps, which is just p primorial. So you can see we've looked at examples up to 5 and then 7. 7, the length of the cycle of gaps for 7 primorial will be 48 gaps, and those will sum to 210. At 11, the length is 480 gaps, whose sum is 2310. And you can see then for 13 and 17, both the length and the span grow super exponentially, faster than an exponential function. So there is a recursion, a 3-step recursion that produces the next cycle of gaps from the current one. This is really important. So far in looking at the cycle for 2 and 3 and 5 primorial, what we've done is run Eratosthenes sieve and then observe the cycle of gaps. With the recursion, we can just work inside the cycle of gaps. So suppose we have an existing cycle of gaps for the prime pk. First step, the next prime is the first gap plus 1. Second step, we concatenate that many copies of the current cycle. And then the third step of the recursion, we fuse. We add together the gaps, G1 and G2, and thereafter add adjacent gaps at the running sums indicated by the element-wise product, new prime times the current cycle. So what are these fusions doing? When we eliminate a multiple of the new prime, when we take that number off the list of candidates, the gaps on either side fuse together into one longer gap. We add those two gaps together. Let's do an example. Let's use the cycle for 5 primorial and derive the cycle for 7 primorial. First step in the recursion, the new prime is 6 plus 1. That's 7. So then we concatenate 7 copies of the cycle for 5. There are 7 copies of the cycle for 5 primorial. Then we fuse. We fuse at between the first 2 gaps, and then we fuse at the running sums indicated by the element-wise product. So the element-wise product, 7 times 6 is 42, 7 times 4, 28, 7 times 2, 14, then 28, 14, 28, 42, 14. And now from the first fusion, we run along and get the running sum until the total is 42. We add there, and that addition between the 2 and a 4 gives us a 6. That's taking 49 off the list of candidates. We run another 28, fuse there, that 4 and 2 give us another 6. We run 14, we fuse there, that 2 and that 6 give us an 8 in the result, and we continue across the cycle. The resulting cycle for 7 has 48 gaps and a span of 210. Note that the last running sum, that 14, wraps around the end of the cycle back to the first fusion. And it better do that, right? This is a cycle, so it has to align that way. So for that last running sum of 14, we have 6 plus 2 is 8, plus that first 6, there's the 14, and we're back in harmony with the cycle. This is taking the cycles of gaps with this recursion. This is the discrete dynamic system. That's what we're going to be looking at. So like any discrete dynamic system, we're going to pick some prime to get our initial conditions. We're going to start with some cycle and say, let's start here. The higher prime we use for that first cycle, the more gaps we can model. So there's an incentive to try to pick that number to be bigger. On the other hand, we've seen both its length and its sum are super exponential. So there's an incentive to keep it smaller, right? Actually, there are computational barriers to picking it to be too large. And there we are. So the path ahead, where do we go from here? We're going to model the populations of each gap. So for gaps G, we're going to model how many of that gap are in each cycle. For this we'll use Markov chains and linear systems. That's the family of tools we're looking at. Note that these populations are also super exponential. The populations of all the gaps in the cycle of gaps are all super exponential. So those will quickly get out of hand. Our solution to that is to normalize the models by the super exponential growth. And now we obtain models of the relative populations. And the relationship here is the number of a certain gap in a cycle is this relative population, this weight, times the super exponential growth. And you will see in the next talk that the super exponential growth is prime minus 2 as the factors. And these are the pictures of those coefficients, of those weights on the super exponential growth. So here we see that 2s and 4s are at a constant 1. The system starts over at the right for the initial conditions. The system parameter is 1. The initial prime here is 37. The 2s and 4s are at a constant 1 in terms of their weight. That line up top, that's the number of 6s. We can see that the 6s are already more numerous than the 2s and 4s, and they will, as the primes go to infinity, those 6s will go to twice the number of 2s and 4s. To label a couple of the other curves here, there's the red line is 8, coming up below the 2s and 4s. The green line is for 10s, the gaps of 10, and those will come across, and those will pass up the 2s and 4s, and those will have an asymptotic weight. They will be about 4/3 times as numerous as 2s and 4s. And that blue dotted line is the curve for 12. So when we start in the cycle of gaps for 37 primordial, there will be fewer 12s. Over there on the right-hand side, it's below the 10s and the 8s, but it's going to grow pretty quickly, and it crosses over the 8s, 10s, and it looks like about the time lambda is a little bigger than a half, there will be more 12s than 2s and 4s in this cycle of gaps.